I'm so excited to learn about wastewater. And he just laughed at me. He just thought it was like so ridiculous that I was, he called it my poo-poo classes, that I was going to my poo-poo classes. I'm an engineer and I'm just talking about toilet water. He thought it was absurd, but I thought it was interesting, and so I wasn't ashamed. Hopefully you're not ashamed that you're learning about wastewater. It's highly technical, actually. So a couple of reminders. The assignment that's due today, you've got until 11:59 for that. So I do have office hours after this, but then I also have quite a few academic advising appointments. And so if you have questions, you may have to hang out and wait for a gap between appointments to talk. But I'd be happy to help you if you've got questions. I already had a good question related to the spreadsheet problem and the BOD loading. And the question that I've got on the assignment where I'm asking you to find the maximum and the minimum BOD loading through the daily cycle, it's just a matter of finding the largest and smallest hourly value from that spreadsheet. So when you calculate that, I think it's the last column that has, in terms of kilograms per day, the BOD loading. So just look through the daily cycle. When is it the highest kilograms per day that you're putting into, well, I guess it would be the outflow loading and the inflow loading, looking for the maximum and minimum of the inflow versus the outflow. So anyways, if there are other questions, let me know. Also, Monday before class, the Part 1 research project write-up is due. Just as a reminder, I'm not interested in ChatGPT's take on this topic. I want to know your take on the topic. So it's your job to kind of go out there, do some reading and research about the topic that you've selected, find references that describe the current state of practice for the topic that you've selected. And then Part 2 is more focused on where are things headed for the future? What are the new developments, the new technologies? Like, what are they trying to improve or change? So Part 1 due on Monday. Question?
When you talked about the Part 1 the first time, you mentioned you don't want any sort of overview or identification of your topic at first. You want us to get straight into the summary of the current situation, like a type of introduction to what your topic is.
So let's say, what is your specific topic?
Hazardous waste.
Hazardous waste. So yeah, I guess what I mean by that is I would want you to focus on, like, how is hazardous waste being addressed right now? And don't tell me, like, what is hazardous waste, but more it's like the engineering applications of how is it being treated or how is it being isolated.
Okay.
All right. Other questions? It's a little stuffy in here, isn't it? I think the building system just has trouble when it fluctuates between cold in the morning and warm in the afternoon. We've got a treatment plant tour next Wednesday. And then anybody know what we're doing on Friday? Exam. Yeah, it's not intentional. By the way, some of you are also in hydraulics. We have the exam on the same day. That's just a coincidence. I just kind of look at where the topics suggest we ought to have an exam. So if you've got 2 exams in one day, I'm really sorry. I've got 2 exams in one weekend to start looking at, so we both suffer from exams, unfortunately. All right, well, we're going to continue talking about primary treatment today, and I've got an in-class exercise addressing clarifiers we'll go through, and then we're going to talk about sludge, activated sludge. So this is where we're at in our kind of discussion of the wastewater treatment process. Remember, we already talked about pre-treatment, which is policy efforts and public education campaigns meant to keep hazardous and harmful materials out of the treatment system. And we talked about preliminary treatment, which is the removal of things through comminutors, grinders, screens. And so we talked about like the grit chamber, and we talked about flow equalization basins, and today we're going to focus on 2 things. Primary treatment, and that's just the first clarifier that the water encounters, where any solids that can settle to the bottom will be removed as a primary sludge. Any remaining grease that will float to the top, or foam, is collected and disposed of. And then we'll talk a little bit about secondary treatment today, and we'll also continue in class on Friday to talk about secondary treatment. So the objective in primary treatment is to remove any solids that we can. Typically you'll remove about 60% of the suspended solids through that primary clarifier, and a little bit of the total BOD load, 30%. It's not negligible. But most of the BOD that exists in wastewater is dissolved. It's not suspended. Or at least the particles are so small that they won't settle in the primary clarifier. So that's why we need to have secondary treatment, is because without it we wouldn't be able to remove an appreciable fraction of the BOD. So secondary treatment, which we'll start on today, there's just a variety of ways that we're trying to bring microorganisms in contact with the substrate in the wastewater and providing for them all of the oxygen that they could want to break down the food as quickly as possible. So their food, their substrate, is just leftover organic material that, if left untreated, would go into the river and would cause a sag in the dissolved oxygen. By the way, wouldn't it be a perfect test question if I gave you this figure and I ask you to define what is number 1, what is number 2, what is number 3, and so that you'd be able to say, like, screen or bar rack. You'd be able to say grit chamber. You'd be able to say primary clarifier, sludge digester, aeration basin, secondary clarifier, disinfection. That would be a really good test question. Just tangent, unrelated to anything in your future. All right. So primary treatment is a settling basin. We've talked about settling before in the water treatment aspect of the course. You know, we're just trying to get things to fall to the bottom through liquid. And we've talked about Stokes' law when we were discussing grit chambers. But Stokes' law really doesn't describe what's happening in a primary clarifier or a secondary clarifier, because it's not free-floating particles. It's more of like a layer of sludge that's falling downward. So we can't just use like a first principles approach at settling to estimate the velocity of the particles as they go downward and the travel time, like the sorts of things that we did for a grit chamber, where we're actually trying to predict the speed of the sand particle as it goes down through the water. We wouldn't do that in clarifiers. We have to use other, like, lab-based techniques to figure out how quickly layers of sludge are settling and compacting. So we'll get into that. But as far as design, what we do is we just use these rules of thumb of how much water it's safe and appropriate to load into a clarifier in terms of cubic meters per day for surface area of the clarifier. So a settling tank has two purposes. It's to settle solids to the bottom, and it's to allow things that are light, like grease, oil, and tennis shoe insoles, to float to the top, and then to somehow wipe the top of the water, to skim it with a boom and collect that and dispose of it through either landfilling or digestion. So some of the important design considerations are the flow rate that's coming in and trying to baffle it so that we create what we call a quiescent settling zone. Quiescent means calm. It's the opposite of turbulent. So turbulent means that there's like a lot of aggressive mixing and scouring, and it's not appropriate and advantageous for things to be calmly going down through the fluid. So if you looked at when we were visiting the wastewater treatment plant, the clarifiers looked like like very still water in comparison to the aeration basins, which were roiling and mixed, and there was a lot happening in the aeration basins. The settling basins are very calm, and they remove the water off the top using weirs to help have a low exit velocity. And so having a baffle of some sort to ensure that there's no inflowing jet of water, because water is transported from one place to another, typically through either pipes or through channels at high velocities, and so we have to have a way to diffuse the flow without interfering with a quiescent settling zone. So the principles are distributing the flow across a column or across the entire width of the clarifier, creating calm conditions in a settling zone, and that means gradually removing the sludge that falls to the bottom of the tank. So having a very slow moving squeegee of some sort at the bottom, or if it's like a chain driven scraping system, the mechanical wiping is usually moving very slowly, and minimizing exit velocities with a weir. So we can either have horizontal flow clarifiers or circular clarifiers where the water is moving upward and the particles are settling downward. In either case, the way that we look at how much we're putting into the clarifier is with overflow rate. Sometimes it's called a loading rate, and we've seen this before where it's just simply the flow rate divided by the surface area of the clarifier. So the area that applies there is the bottom area of the clarifier. So like top view, what's the area of the clarifier? That would be the units here of meters square in the denominator that we're using. So the water doesn't spend a lot of time in the primary clarifier, maybe an hour and a half to 2.5 hours would be a typical hydraulic detention time. And oftentimes the flow would be split up into multiple parallel streams. If you have so much flow coming in that it would mean the basin's any longer than 100 meters, and that would be a really, really long clarifier. Probably very few would be as long as 100 meters if they're rectangular. And in terms of the diameter of clarifiers, it would be unusual to have a clarifier going over 100 meters in diameter. So sometimes you need clarifiers to be operating in parallel, where what you're doing is parallel means that the flow is coming in and then it's being split. So it may be that we've got several different clarifiers, each which are receiving a portion of the flow. And the advantage of having parallel streams is that for maintenance purposes you can shut one of them down and still send flow through the others. That would be much better from an operational standpoint than having one gigantic clarifier. So there are periods when the flow is low, periods when maintenance needs to be done, and it's just better from the standpoint of redundancy to have parallel streams rather than one big clarifier. So here's how we calculate the loading rate. It's the flow rate coming into the clarifier divided by the top view area of the clarifier. So here's a side view of a circular clarifier where the water is flowing up and the solids are settling down, and then there's also some sort of like a boom, a floating boom at the top that's collecting oil and grease. So the sludge that comes out is either being dewatered through a belt press where they're squeezing the clarifier and squeezing the solids that are in the sludge and trying to separate them from the liquid fraction. At the treatment plant they talked about dissolved air flotation, which is a way of trying to separate the liquid in the sludge from the solid components. We just, if you take sludge from 1% solids to 2% solids, it doesn't seem like that much of an increase, just increasing the solids from 1% to 2%. But what it does is it decreases the volume you have to dispose of by half. So you're cutting the volume in half if you can increase the solids concentration by a factor of 2. So circular clarifiers, the water flows radially outward towards the weir at the end. And in the case of a rectangular horizontal flow clarifier, then the water flows horizontally as the sludge settles down. All right, I've got a handout for you today where we're going to look at some calculations of the primary clarifier and analyzing an existing system that's in place. So this existing clarifier, there's actually two of them in parallel. So the flow rate that's described here, 1.2 cubic meters per second, it's split. So we've got a flow coming in, it's split, and we want to know if we calculate the overflow rate for this scenario, how does it compare to the typical guidelines of 25 to 60 cubic meters per day per square meter? So let me write that on the board. 25 to 60 cubic meters per day per meter squared of clarifier area. That would be like considered typical loading rates. So for here, we've got two 35-meter diameter clarifiers. And so you're going to need to calculate the area of each clarifier, which is going to be pi d squared divided by 4. And then the flow rate that's going to each is the flow rate total divided by 2, because we're splitting the flow into two streams. So calculate, I'll pause for a moment here, let you do these numbers, find out what is the effective flow rate for this situation, and then if the clarifier is 3.2 meters deep, how long is the water spending in the clarifier? The hydraulic detention time, theta sub h, is the volume divided by the flow rate. Because volume is cubic meters, flow rate would be cubic meters per day. So if you divide them, then you end up with units of time. All right, so let me pause for a moment and give you some time to do these calculations. Okay, so the water comes in and it's split. So it's 0.6 cubic meters per second that's going into one of them, and 0.6 cubic meters per second that's going into the other one. Each of them have a diameter of 35 meters. So the loading rate into each of them, we have to know the flow rate, 51,840 cubic meters per day. You know, if we multiply by 86,400 seconds per day, then we get that. And we need to know the area of the clarifier, because the loading rate is just the flow rate on top of the surface area of the clarifier. So 53.88 meters per day, and that puts us towards the high end of the normal range, but not out of the ordinary, between 25 to 60 cubic meters per day per meter squared. So if we look at the units here, I can also express cubic meters per day per meter squared as just meters per day. So that's why they call it like a velocity, when really it's not a velocity, it's a loading rate. And this although it has units of velocity, it doesn't physically represent like the speed of settling downward. It's not that at all. It's just maybe not coincidental, but don't be distracted by the units of this loading rate in thinking that that's actually the velocity of something that's happening inside of the clarifier, because that's not the speed of anything downward. So this is okay from the perspective of the typical loading rates. It's within the guidelines, yes. The hydraulic detention time is a little bit less than average. I told you that usually water spends between 1.5 and 2.5 hours in the clarifier. In this case, because the volume is 3078 cubic meter for each of the clarifiers. So the hydraulic detention time, I'm going to use the volume of one clarifier and the flow rate that's going into one clarifier. You'd get the same value if you did the combined volume of both clarifiers and the combined flow rate that's going into both clarifiers. But the residence time isn't we're not adding together the residence time of each clarifier because it's not in series. If it was one clarifier after the other, that's series, then it would be additive. But here, since they're in parallel, the residence time of one of them individually is the same as the residence time of both of them together, because the water comes, it's split, and it's just spending about 1.43 hours in each. So the water is being clarified for 1.43 hours, regardless of whether we look at one of the clarifiers individually or the sum of them together. So any questions so far about these calculations? If the inflow BOD is 250 and the removal efficiency is 35%, then how many kilograms per day is removed by the entire system? So the answer it's asking for is a mass flow rate. So mass flow rate is concentration times volumetric flow rate. So they want to know mass flow rate as units of kilograms per day. And concentration as units of either milligrams per liter or grams per cubic meter, which coincidentally is the same because there's 1,000 milligrams in a gram and there's 1,000 liters in a cubic meter. So if I tell you it's 250 milligrams per liter, it's also 250 grams per cubic meter. Okay? So, and then volumetric flow rate is units of cubic meters per day. So, if we multiply, mass flow rate is concentration times volumetric flow rate. So we want to know how many kilograms per day is being removed if 35% of what comes in is being extracted by this clarifier. So we're told it's 250 milligrams per liter of BOD that comes in. So that's 250 grams per cubic meter as well. And it's removing 35% of that, which means it's removing 87.5 grams per cubic meter. So for every cubic meter of wastewater that comes in, it's removing 87.5 grams of BOD. So in a daily cycle, if that's 103,000 cubic meters of water that's going through the clarifier, then that means the amount of BOD that's removed in a day is more than 9,000 kilograms of BOD. Now, it's not like that's coming out as a solid at the bottom of the clarifier. Remember, what comes out of the clarifier is sludge. So it's going to be BOD and water that is together in that sludge at the bottom. But this is just assuming that we get 35% removal of the BOD that's coming in. So any questions about the part D calculation there, how we find the mass flow rate of removal? I'll leave that up for a moment in case, yeah.
The total flow, you used the 87.5?
87.5 is that's the fraction of the incoming BOD that's removed. And then we use the total volumetric flow rate like for both clarifiers because it's saying how much is removed by the entire system. That means like by both clarifiers together. So if the good point, by the way, if this had said is removed by each clarifier, then you would have just multiplied it by the flow rate that's going through one of the clarifiers. But this said how much BOD is being removed by the entire system, meaning both of the clarifiers together. Does that answer your question? All right. Other questions? For a lot of years, all they had was primary treatment. And then they just dumped the water from the top of the primary clarifier right into the river. and let the sag curve do what it does. Like if your BOD goes too low, if there's too much BOD and it causes the river to have like a bunch of fish kill, then they'd shrug their shoulders. Too bad. That's life for the fish. And that's kind of disgusting, and it would, if it's not disinfected, then actually at the treatment plant, I think I remember him saying that when they only had primary treatment, they were disinfecting, and they were using, I think he said more than 10 times, I think it was like 10 or 20 times as much chlorine then as they do now, because there's just was so much BOD and so much organic material that would neutralize the chlorine. So by adding the secondary treatment, they reduce the amount of chlorine that they're using. So secondary treatment is all about trying to remove the BOD that remains. The primary clarifier is only removing about 35% of the BOD because most of the BOD is dissolved or is suspended in particles that are so small that they won't settle in the primary clarifier. Like really, really small particles, they're not going to settle in an hour and a half, 2.5 hours. It's just not enough time for a really small particle to settle downward. So they make it through primary treatment and they go into the aeration basin, and we've got to do something with all that leftover BOD. BOD, remember, is the food for bacteria. It's a substrate. It's their energy source. And if we let it get into the river, then they'll consume it in the river, use up all the dissolved oxygen in the river, and it's unpleasant for us, bad for the environment. And also, we want to remove BOD and suspended solids because then the effluent water quality is safer for the communities downstream. So secondary treatment, we're trying to remove BOD and suspended solids, both. And the way that we're doing it is through enhanced biological activity. We're trying to stimulate the bacterial activity by providing them an environment that's suitable for breaking down the waste. And so what do we need to accomplish this? We need microorganisms. And they talked when we visited the treatment plant about how their aeration basin got washed out. He called it washed out. That just meant that the flow rate was so high during the recent floods, there was so much stormwater coming into the treatment plant that they basically just had to open up the valve, and the flow rates were so high that it took their bacteria and kind of just flushed it into the river. So it takes them a couple of weeks to get things going again. When they try and retain some of the sludge. They'll stop recirculating and they'll just keep a fraction of it so that they can recolonize the aeration basin and the secondary treatment after an event like that. But having a lot of microorganisms is important, and there's not enough microorganisms in raw sludge. You need to have in raw wastewater that's coming into the treatment plant. So, there's definitely microorganisms in wastewater, but we want there to be even more than there ordinarily would be in the inflowing wastewater, and that's why we recirculate sludge. Having good contact is accomplished through mixing with either some sort of mechanical mixing, meaning like impellers or paddle wheels, or by putting aeration, which can also cause physical stirring of the aeration basin. We want to do things to make sure that there's enough oxygen for the microorganisms. And then it's also temperature dependent. The warmer it is, the faster this process will go. And we won't bother to heat the wastewater because that would be cost prohibitive. But we are aware of changes in temperature, and so when we're doing design, we want to make sure that our system will be effective at the lowest temperature we're likely to see during an annual cycle. And we also have to design enough time for the microorganisms to do their thing. So there's a lot of ways to achieve secondary treatment, and a lot of these are really interesting. I love trickling filters, for example. I've seen trickling filter at some treatment plants. We'll talk about it a little more, but what it is you're basically spraying wastewater over rocks or plastic media that bacterial colonies will grow on the outside surface of rocks or plastic, like little plastic pellets. And so you're kind of spraying this slimy colony that's going to reach out and grab some of the BOD as the water's trickling through it. We'll talk more about that. It's a fascinating process that can be really effective when conditions are right. Oxidation ponds are just large tanks, essentially, where water spends a lot of time. It's kind of a low technology thing. Rotating biological contactor, that's what RBC stands for. Rotating biological contactor. It's just another way of bringing bacteria into physical contact with substrate and oxygen. But activated sludge is the most common way of achieving secondary treatment, where we're trying to remove BOD, remove suspended solids. Activated sludge is king. It's the most common, it's the most generally cost-effective, and so we'll talk about it. Here's a diagram that illustrates what's happening in activated sludge. So why is it called activated? Like, what's so activated about the sludge? So this is the secondary clarifier. We already had primary clarifier. It's not pictured. So the water comes from the middle of the primary clarifier and into the aeration basin. In the aeration basin, look at what's coming in. Air is coming into the aeration basin. It's being pumped through blowers. And when we visited the treatment plant, they said that they don't let us go see the blowers. Does anybody remember why we didn't get to go see the blowers? They gave a tour a couple of years ago of the blowers, and like 30 minutes after they had a tour go through there, one of the blowers blew up. So they're like, these blowers are a little dangerous. Let's not take tour groups through there anymore. They had the fire department out just kind of getting the lay of the land, and 30 minutes after they left the blower room, one of them exploded. So we didn't see the blowers. But the blowers are providing oxygen to the aeration basin. What else is coming in? So there's water coming from the primary clarifier, and then there's sludge, recirculating a fraction of the sludge from the bottom of the secondary clarifier. And it seems like no big deal, like, okay, there's the sludge, it's going in, but I promise you, it's one of the big ideas of civil engineering. I've said before, it's right up there with introducing steel reinforcing into concrete, which made it possible to start making buildings with concrete once they decided, well, we could get both compressive and tensile strength if we put steel reinforcing in concrete. That's like the best of both worlds, right? Here, the best of both worlds is you are aerating the wastewater to provide the oxygen they need, but you'd have to do it for weeks and weeks if you didn't also introduce this sludge. You'd have to have tanks so big they would take up like 20% of your town. That's how long it would take. You'd have to store the wastewater for weeks, except for the fact, and the reason you'd have to store it for so long is that there's just not enough bacteria in regular wastewater to break down all the BOD. There's too much food relative to the number of microorganisms that are there. They couldn't eat it all in a short amount of time. What somebody realized is, well, if we take some sludge, that has a lot of bacteria in it. So if we pump the sludge into the aeration basin, then suddenly we have control over the number of microorganisms that are in there trying to break down the substrate, trying to use up and eat the BOD. So it dramatically reduces how much time it takes from weeks and months to just hours, or at the outset maybe a couple of days to break down all the substrate that we want to remove here. So activated sludge, it's activated because when it settles to the bottom of the tank, it gets hungry. The sludge down here at the bottom of the secondary clarifier, these microorganisms that are waiting to be pumped back into the aeration basin, they are starving. And so when they get to the aeration basin, they are just ready for the buffet, and they go for it. And the rate of utilization is very fast. So the reasons why we circulate sludge is, number one, to have more control over the ratio of food to microorganisms. So this F to M ratio, the food is just how much BOD is coming in. We can't control that. That is related to the conditions that generate the waste. It's related to how much infiltration and inflow there is, whether you've got combined sewers and so on. But we can control how many microorganisms are in the aeration basin if we increase or decrease the amount of sludge that's going in there. We also do it to control how hungry the bacteria are when they get into the aeration basin. So we can leave them in the settling tank for a long time and they'll just be absolutely starving. And of course, there's a limit to that. If you leave them too long, then they'll die, and that's not effective anymore. But you know, how long we leave them in here also kind of preps them for the removal of nutrients, because when they're stressed and don't have enough oxygen and food, then they go into these conditions that make them more prone to removing nitrogen and phosphorus, in addition to consuming BOD. Now, I have to point out that a portion of the sludge is wasted, because if we only recirculated, then the amount of sludge would get more and more and more and more, because like the bacteria, when they eat dissolved BOD, that's turning something that's liquid into something that's solid. It's just like if you drank sugary Gatorade all the time, you'd gain weight from that. Well, the microorganisms, they're consuming dissolved BOD, and that's increasing the amount of cellular mass in the system. So if we didn't waste some of the sludge, then there'd be an accumulation of solids in the system. So there is a fraction of it that must be wasted. So this is the microorganism life cycle. Initially, in the lag phase, microbes are kind of just getting a foothold. They're not very biologically active. They're getting accustomed to the environment. They're not using a lot of food while they get accustomed to the environment. So on the vertical axis here, it's just the number of bacteria. So for the first several hours, as they're getting acclimated, the population doesn't increase very much. But when we enter this exponential growth phase, the cells, they're dividing very quickly because they are in an environment that has an abundance of food, an abundance of oxygen, and so they're very quickly growing their population, and they're using the substrate, meaning the BOD, at a very high rate. If we left them in the reactor for a long time, eventually there is either a buildup of waste byproducts or the availability of food would decrease. And so the population is no longer growing in this stationary phase. And then finally, if we didn't bring in fresh food or provide fresh oxygen, or if we didn't carry away their waste products, then there would be a death phase where the population is actually going to be decreasing. So this is if we put microorganisms into a batch reactor. A batch reactor doesn't have any flow in, it doesn't have any flow out. So if we had just a closed tank with food and microorganisms, this would be the life cycle that they go through. So, which part of the life cycle do you think is most efficient in terms of removing BOD? We want to be in this log growth phase. We want to have exponential growth, because that's the phase where they're dividing quickly, where they're using up substrate at the fastest rate. So when we are trying to design activated sludge, we have to do lab tests to try and find out, for the microorganisms that we're likely to have colonize a wastewater treatment plant, what sort of temperature conditions, what kind of F to M ratio, food to microorganisms ratio, like what are the conditions that allow them to be in that log growth phase where they're dividing really quickly. Because what we want to see is we want to see the population growing fast, because if the population is growing fast, that means that they're breaking down the food very quickly. So the model for population growth, they divide. It's called binary fission. One microorganism splits into two microorganisms divide into four. It's not like they have traditional birth, like mammals do. They just divide in half. So with each generation, you're doubling the number of microorganisms that are in solution. So here's the formula that N would be the number of generations. And so your initial population multiplied by 2 to the N will tell you what the final population is. We'll skip over this example. Actually, we're out of time. I think I've maybe kept you over an extra minute the last few class meetings. So today I'm going to start paying you back. 1:49. We'll finish 1 minute early and pick up here on Friday. Some of you will be gone at the Virginia's conference. Please be sure to watch the video so you don't fall behind.